being like all sweaty because it's still warm out and you're wearing
sweaty?
a raincoat and you're like walking.
Oh yeah, yours are
so
wet. It's
that
wet,
feeling
yeah.
of being like so wet, like under my neck. It's been like a year. So
That's pretty good.
does anybody have? Oh, you're recording. Okay.
I am.
All right, we can probably do something. One second. It's not like I really prep, but I think I know what I'm talking about. So see how it can go, and then we can do a little bit more, less structured Q&A based stuff. Two conversations that I want to start to have today. 2:40 yet? No, we don't want
The nuclear survival seminar?
No.
Oh, okay. Because I heard that one was really hard.
It's tough on questions, but
It was really hard. No? I don't remember who told me that it was hard. I went into it thinking it was going to be totally different. Because I guess I'd never heard of it all along.
no, there's classes about information theory. I think it's just a lot of like stuff.
Okay. It's all downhill from here.
Thanks for coming, everybody.
Woo!
You know what's weird is that I wanted to thank the people who came to my office hours today. Oh no, but there's almost empty intersection between the attendees at my office hours and the attendees. Thank you. But some people attended, not my office hours, my lab meeting this morning.
Oh,
You're all welcome to attend my lab meeting. By the way, if you're interested in the research that I'm doing and you're interested in getting involved in research, I realize that this is too little too late for many of you who are like about to graduate, right? But my lab is called Disorderly Labs, and we meet in E2 398, aka the LSD lab, Languages, Systems, and Data, at 10 a.m. Wednesdays for the time being. So you are all welcome to come and be a fly on the wall and see what we're talking about. There's a little bit of a type and naming problem that there's one LSD lab, singular, that I share with some of my colleagues, and my lab is Disorderly Labs, plural, which is contained in LSD lab, singular. So that's a little weird, but what are you gonna do?
cool.
Also, incidentally, I am Palvero on Twitter.
We all know.
Did you get verified because you know the person who does the verification?
Well, no, you get verified. Verification is like fame. It happens for arbitrary reasons.
Okay.
And I think in my case it was like, I am a professor. You know, so I remember when I first got verified, I was like, why are you verified?
I don't know if Owen's verified though.
What?
I don't think Owen's verified.
Yeah, I mean, he may not have requested. And it's like,
Oh, yeah, you requested.
You know, not to be like, if I can boast for a minute, it's not just based on, it's
Clout.
also based on whatever how well known they think you are.
Mhm.
Like that. So, I don't know, popularity is weird. But I think popularity contests are great if you're popular. So today, thanks for coming, everybody. And again, yeah, so come stop by my lab anytime. I want to, we're a skeleton crew, so we can go slow. And conversationally, and I'm not super prepared. But these are the things I would like to begin talking about, transitioning into a world in which we've addressed issues of consistency that arise when we begin making multiple copies of the data at record. Now that we understand very well that all the things that can sort of go wrong, we can now permit ourselves to begin asking, what can go right? Right? Like, why are we picking up lots of computers? Very often the answer is not just because we want our systems to be more resilient, but because we want them fast is a colloquial term, right? But we want to increase the throughput that our system can handle. We want to increase the capacity that our system can handle. And as we all know from parallel computing, sometimes doing things with more resources means we can do the same job faster, or we can do increasing amounts of work as we scale up our resources. So I wanted to spend a little bit of time in the beginning of the class talking about, just as we talked about some of the ways that we quantify resilience, let's talk about some of the ways that we quantify adding computers to make stuff go fast. Okay, and so the first concept I wanted to talk about, the first definition I wanted to get out of the way, is this concept of speed up. Everybody have a nice, handy working definition for what speed up is? Obviously, it's something we want. We want to be able to have good speed up. Yeah.
So speed up is compared to some other thing. It's comparison.
Yeah.
How much less time does it take? So if something takes twice as much, if something's twice as fast, look what it is, something else, you might say that's two speed up.
Yeah. So usually when we talk about speed up in the context of parallelization, the thing that we're comparing it to is the sequential version of the job, right? So how much speed up do I get taking an algorithm that was designed to run on one computer and running it on k computers? And how do I reason about that as a function of k? Right? So what kind of thing so we might plot speed up very naively as our x-axis is just the number of parallel resources. And obviously, if we're in an architecture class, what we're scaling up down here might be cores on a single die or something like that. Of course, in our world, this might be rack mount 1U servers that we're adding to racks in a data center. And now these are different. And we'll get into the difference between when we talk about distinction between scale up and scale out. Bottom line is, we want to know, given a fixed job, how much faster can we go as we increase the number of resources? So if out here we have one, and out here we have, 100 machines, what kind of curve would we like to see? And what's here on the y-axis is obviously like time to complete the job, like walk-on time, right? So what kind of curve would we want to see? Or would we expect? What kind of curve would we want to see?
Linear.
Some kind of linear, I don't know, zoom. But obviously that doesn't make any sense because then, obviously we're not going to be actually taking negative time to do the job. So what would we actually expect that curve to look like? Well, it'll clearly level out somewhere. And we think I guess the expectation is it has to level out somewhere and it's going to basically get to a point where it's not doing any better at all. Because if it didn't get to a point where it wasn't doing any better at all, it would converge eventually, maybe way out here. So we know that there's no way we're going to converge to 0 time. Mm-hmm. Why? Why in the limit won't it take an arbitrarily small amount of time to do that one? So there's one fixed job. There's this job X. And if I do it on one machine, it takes, an hour. And down here, there's like a second. Why do I think I won't ever get to that? Yeah?
For every job, there's at least some overhead, at least
Yes.
starting it.
Yeah, another way of putting that is that overhead can mean a lot of different things to a lot of people, but for every job, there's some part of it that can't be divided up into pieces and solved in pieces. If only the labor of breaking the job into pieces and then combining them at the end. A lot of times it's worse than that, but at least that part, right? So I have this piece of work, X. And if I want to run it on 10 computers, at the very least, I'm going to need to break it up into 10 pieces, put it on 10 computers, process very fast, and then combine the results. And so this part and this part of the algorithm, if nothing else, are not going to be improved by adding more computers. If anything, they might actually go slower. There's more upgrade. Right? That's why we get the sense that this curve might not be so good. In fact, if we're not careful very often, this curve just looks like that. And that sucks. Right? That means you should probably just use 2. Because you got a marginal benefit from using 2, and no marginal benefit from using 4. Okay. So we'll get to this in a minute. This is colloquially known as the law of diminishing returns, or Armdahl's law. We'll talk about informally and pictorially, since you've all seen it before in the context of computer architecture. So that's speed up. We would like obviously we like this. It would be great if we could get an S-curve like that. In practice, it probably looks more like this, unfortunately, unless we're very cunning. Make sense? Scale it. Speed up right there. What about scale up?
Is it the ability to handle larger and larger amounts of data efficiently?
Yeah, I mean, it doesn't necessarily have to be data, although it almost always is in the kind of data-intensive applications that we study in a distributed systems class. But it's like, let's say you don't have a fixed workload X. You have X of n, where n is increasing. Like, this is the way we usually think about algorithms, right? As we increase our data sizes, what is the expectation of other performance? So the way we would plot that is, we're actually going to plot workload and resources on the x-axis together. The idea is as we move right on the x-axis, we're adding more computers and linearly adding to the size of that in the workload. And here's time complete. And what kind of curve would we like to see? What would we call perfect scale up?
Flat line?
Yeah, with flat line, I don't really care where it is, right? Because it's like, if I can do with one computer my batch job in an hour, that's cool. But I want it to be the case that if my batch job is like computing my revenue from yesterday on my website, it's not going to be okay if, as the workload goes up, we get out to somewhere out here that's more than 24 hours. Because then I'm going to get yesterday's report tomorrow, and today's report 2 days from tomorrow, and so on and so forth. Right? That's not, in fact, I've been there. I used to be an Oracle database administrator for a company that had this problem. Our ingest rates were growing, and our scale up was not good. And it got to the point where, you know, you got yesterday's report right before you went home for the day at 4 p.m. And you're trying different things. So yeah, you would like it to be, you know, straight. That would be perfect scale up. That I can take n to infinity, and as long as I have budget to take my servers to infinity, it just takes an hour. That's awesome. What do you think it really looks like?
Probably
It's hard to say, right?
Yeah.
It's hard to say because some algorithms have great scale up. You've already sort of paid your sequential costs. It's already included in this number. So it's not completely unthinkable that you could go out for a long time. But there's going to be some limit where it's like, suddenly it's the network and not the servers. There's going to be some bottleneck that comes out of your control where you start falling off. Just hopefully that it's far enough out here that it's a workload that you'll never get to. That's what we would expect. Say again? Sorry, so go up. My bad. Yeah, exactly. That you're like, oh crap. Because now we're not getting the same benefit for every server we add because we've introduced other bottlenecks in our infrastructure.
Would that line ever curve up and down, like fluctuate up and down?
Absolutely, maybe, I don't know. So this is like a really hard one to predict, because like, it's very often the case that, you know, in conference papers, you'll see these graphs and they're like, our system is totally scalable, and here it is, like, look, here's 12 machines, man. We like scale perfectly. And you're like, dude, that's 12 machines. Like, I could put them under my desk, you know, like, who cares? Like, what I would much rather see is the inflection point of where it goes wrong. Like, what is the bottleneck and how far can you push this thing is a much more interesting piece of information for me. Even if I think I'm never going to be out in this regime way out here, I want to know where my assumption that adding resources linearly as the workload increases linearly is going to stop providing me with benefit. Okay. And then do you have a sense, and this is a really fussy distinction that we're not going to focus on much in this class, but the distinction between scale up and scale out? Yeah.
So the way it was explained to me is scale out is increasing your resources in terms of like instead of one computer, 2 or 4 or 8 or whatever. And scale up is instead of one little computer, using one really much better computer.
Yeah, which might just boil down to like cores on the computer versus computers. But it could be more subtle than that, because you need like enterprise class buses to handle the communication, blah, 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 blah. Okay, so that's absolutely right. Did everybody hear that? So like, they're the same thing, except scale out is like, the resources are computers, and scale up is the resources are a single computer that is becoming more enterprise class, more
I see.
cores,
Oh,
more
I see.
memory,
Oh, I
a
see.
bigger computer. Which is better?
I don't know.
Depends on
Depends on what. Yeah.
workload.
If you care about cost, obviously scale out is going to be.
Scale out's way cheaper, because as we discussed a bunch of times in this class, you're looking at super linear. You can imagine saying workload and resources and dollars if what you're doing is scale out. Linear cost, linear increase in resources, linear increase in workload, as opposed to you couldn't plot scale up this way because your cost would be this other thing,
Yeah.
right? Or even super linear, right? So that's a reason why scale out is better. Why is scale up? Like, is scale out always better? Should everybody just do scale out, or is scale up sometimes better? What is time scale anyway?
Yeah.
Is it scale up or scale out?
It's scale up.
It's something that looks like scale up,
Yeah.
but
It uses-
costs like scale out.
Yeah. so
And I
that-
really wonder where that thing falls off.
Right. So it uses scale out to build a hyperkernel that scales out.
Yeah.
And so it uses resources that you would apply to a scale out solution in order to.
Give the
Yeah.
users or the customers something
Yeah,
like so.
yeah,
But what's
so-
so good about scale up for the customers then? What's so good about?
The example for me that was applied a lot was if you're like Amazon or something and you have a database, it would be really nice if you could fit more of that database on one machine and not have to deal with consistency ever, or consensus ever.
And that's
Because-
exactly what I would say. Is
Yeah.
that okay? So this costs more, and you can only scale up so much. There's like a point where here's a credit, and it's game over now. You can't get any bigger than that, right?
Totally.
It means that, go back to like the first day of this class. It means that an algorithm that was designed to run on one computer will just run, irrespective of the input data, on something that appears to be one computer, without you having to deal with asynchronous networks, partial failure, consensus, replication, retry, all the things we study in this class, you don't have to do in a scale-up regime. So that's huge.
I have a fun anecdote.
Okay?
There was a use case of using R to do some statistical modeling in order to certify compliance with some state law. And they would do a run, like it's a business that their business model is they run this, right? And a month later it finishes, and then they submit that to the state, right? And TitlesCale sold them a POC, and because they were a bigger system, they were able to change some of the ways that the R algorithm worked, because R is kind of idiosyncratic, and they ran the model in a day.
There's a nice piece of work it's pretty old now, it's probably about 10 years old, called RiotDB. You ever heard of it? The idea of RiotDB is, hey, R is this neat thing, because a lot of people do scientific computations in R, but R is designed to run on one machine and to run in memory. Wouldn't it be cool if you could have a backing database and have R just intelligently page out to the database so that it appeared to be running in memory, but it could actually do have as big of a working set as you could fit on disk? It's just a similar thing. Presumably in that case it would finish in 2 weeks and not an hour or something like that. Okay, so speed up, scale out. These are all ways that we measure the benefit of adding more computers to make things go faster. Questions? Feel confident with that? Awesome. Let's talk for a minute about Amdahl's law. Let me see if I can write the formula, because it's the kind of thing you should be able to do from first principles, but I panic whenever I see formulas. Let me see if, you all know I did my degree in English literature, right? So,
Yeah.
not my graduate degree, they wouldn't give me the job, but my undergraduate. So what is Amdahl's law? Amdahl's law is a way of thinking about the degradation of our speed up curve, right? Like, what are the limits to how we can make things go fast by using a great many computers? And the intuition, as we already discussed, is that no matter what computation you dream up, there's going to be a portion of that computation that's fundamentally not parallelizable. That fundamentally, it's not so much that it's not parallelizable, but there's no benefit from parallelizing it. You don't make it go faster. Okay? So a way of thinking about this is we want to reason about, this isn't the way you usually formulate an architecture, but this is like the distributed systems way. I want to know that if I have n computers, How long is it going to take me to perform some job? And almost is what's really easy to reason about, right? You say, well, okay, the time it's going to take to run some job, X, on n computers is going to involve what he calls B, okay, which is the part of the computation that can't be parallelized, the sort of startup overheads, plus the time that it takes to run on one computer without that serial part, divided by the number of computers that it takes to run the job. Did I get that right? I think it's right.
I think that's right, yeah.
Yeah, I mean, like you get it a little differently. If what you're trying to compute is the speed up as a fraction, then you obviously manipulate it a little bit differently. But what I'm trying to find out is how many days does it take if I have n, given that I know how many days it takes if I have 1. So you say, okay, well, how long would it take to run on one computer? That's a parallelizable part of the computation, that minus b. So we can divide that by n, get that arbitrarily down by making n big. But then we always have to add back the part that wasn't parallelizable. That makes sense?
Mhm.
And so the visual intuition that I want you to take away from this in the context of distributed systems is just the following, right? So if I have this job in which I have this block B, and then this block t to the 1 minus b, you say, cool, that's great, because like, look at all this shit that we can parallelize. But then you start thinking it through, and you're like, okay, shit, because if I had 2 parallel resources, that would just look like this. And if I had 4, that would look like this. Do you see what's happening here?
Yeah.
And I'm probably not even going to bother going to 8, because the jump from 4 to 8 is going to cost me twice as much money, but get me almost no marginal benefit over the total time.
Right.
We've only exponentiated 2 times. And we've already gotten to the point where the runtime of this job is completely dominated by B. So we should stop. So, oh great, fine, fucking A, you know. 4 computers is a little better than 1, but it's way harder to program.
Right.
So that sucks. Does everybody get it? I mean, you get it, right? That's a drag. So what can we do? All we can do, just as like the smart thing to try to do with software, if you can, in terms of availability, is to make mean time to recover shorter. We want to make B smaller. So let's take a moment. What is B? Yeah.
Splitting up work, putting it back together.
Yeah, so I think like dividing, not conquering, right? Conquering is this part. But dividing and combining. And unfortunately, this would appear hard to shake out. How could you do better with this? I can think of one good answer to this. Like, how could you cut down the B when B is dividing and combining? Yeah.
Scale up the machine it's dividing and something like
I don't know if that's going to work, though. So maybe if the job of dividing work were computationally bound, sure. But my expectation would be that it would be network dynamic. Right? So, yeah.
If your data was already divided up.
That's exactly the answer I was looking for. It's like, well, shit. I mean, let's say that the data was divided in some reasonable way in situ. Well, when does that happen? Well, all the time. Like if you have a database, like I don't know, let's say you're building a scale-out key-value store for homework 4 or something like that, then your data is already partitioned in order to increase your capacity, and it's more or less uniformly partitioned. So that didn't have a big deal. Like there was a good reason for the data to be divided already. And there's better reasons than that. If what you're doing is processing logs, like on web servers, the data's already massively distributed. There's a big ass independent log associated with every machine running a web server on your front end or something like that. The data's already massively distributed. And this is basically the idea behind MapReduce and Hadoop, which we're going to study a little later in this course. We're going to actually read the MapReduce paper. It's that, like, for reasons orthogonal to parallel processing, you've had to smear the data around this system. So there's already all these opportunities to, instead of trying to ship the data to a place where you can compute on it and then pay that shipping cost, you can essentially like ship the compute to where the data already is. Because it's cheap to move a function to some data. Right? Data has, you know, we're talking about data gravity, right? Moving code closer to where some data is already stored in general has a very low overhead. So that's a great way. So let's see, that was what's in B. minimizing B, what are some tricks? One might be moving computation close to data. When you're in a position which you can take advantage of this thing that may or may not be the case, that the data is already distributed. What about combining? I mean, I think the obvious thing to point out about combining is that for some jobs, combining is vacuous. Some jobs, the answer is just the union. Like, I've broken up this job into a bunch of pieces, and I've run on all these different computers. Let's say, for example, that I'm computing word count. And this is like the count of all the words from A to G, and this is the count of all the words from H to da-da-da. Well, in some sense, like, the answer is just the union of all these things. I don't need to combine them if I partitioned it smartly. Right? So sometimes we can do better around combining too. What else is in B? What else is fundamentally not parallelizable? It fundamentally slows down computation in a way that can't be broken up and sped up with more.
The task of allocating, telling all of the other computers or processors.
Wonderful. So I would say at a really high level, I would kind of characterize this as like, in a distributed system in particular, right? Orchestration / coordination. And I would make a distinction between the two, although they're kind of similar concepts, right? I would argue that like orchestration in some sense is always necessary. Like somebody needs to tell which computers what to do, right? If we have a big system, you have to decide what runs where. You can't get around that. I would draw a distinction between orchestration, a necessary thing in the distributed computation, and coordination, something that isn't always necessary. Right? So what is coordination? To me, coordination is a blanket term I use to describe the net effect of using things like Paxos, two-phase commit, locking, any kind of synchronization. Right? The idea of coordination is, I'm a computer, and I have some data, and I have a CPU, and I could compute over the data and produce the result, but I am not doing so, because I'm waiting for some external signal that it's safe to compute on the data. That might be I'm waiting for a lock to be released on the data, or that might be that I'm waiting to know my spot in the total ordering of events. Or it might be that I'm waiting to know the status of a particular commit abort decision, or something like that. But I would draw a distinction between, in some sense, like, I can't compute on data until the data's there. That's fundamental. So as we said, either the data's already there, or the data needs to get moved there. And that's a cost that can't be avoided. However, if I have data, and I decide not to compute on it because I'm waiting for somebody to tell me it's okay, that's a fundamental cost that belongs in B, right? And coordination is, in general, something that can, in some cases, be avoided, right? You looked at this in the context of Lindsay's guest lecture. Like, what if I looked at the data that I was storing in my database, and I determined that what I was modeling was a shopping cart, and a shopping cart has set semantics. Something that has set semantics is going to produce the same results, irrespective of the orders in which things happen. Well, then I wouldn't rub any clocks on that system, and I wouldn't use Paxos, because there wouldn't be any need to come up with a total order, because all orders produce the same result. Right, so for me, one of the big things that you could carve out of B is the unnecessary calls to Paxos, the unnecessary locks and things like that. Did you think of anything else? If there's one thing, actually, I should have dwelled on more in this class than I've dwelled on more in the past, is that, so we studied Paxos at some length. We probably got sick of it. We probably also sort of enjoyed it. What does everybody think of Paxos? Paxos interesting? Worth learning?
Yeah, worth learning.
So the most important thing that I hope you will learn about Paxos in this course is not to use it. And I think that's also the hardest thing about Paxos, even harder than understanding how to implement it, even harder than understanding whether it's correct or not, is understanding when you don't actually need it. Because it gives us these overheads that very often can be masked. Right? That's the hard thing. Determining when a computation can proceed without a total order, and nevertheless produce an outcome that is indistinguishable from one that got that total order. Okay. I mean, unless anybody else have any ideas about what we can do to cut down on the non-parallelizable part of our computation. I think a lot of it really does come down to tricks about like performing some of the stuff that should be in B outside the computation. Having something else have already taken care of some of those overheads so that we can do a massively parallel computation. Yeah. All right, let's talk about how we divide work into pieces. As I mentioned earlier in this class, we can think about dividing resources in a variety of ways, but it is very often and almost always the case that we're focusing on data-intensive applications, data whose performance is bound by, computations whose performance is bound by the size of the input data, rather than the complexity of the computational problem. Now we can think of exceptions to this, right? So you have some machine learning job where like maybe the training set is not even that big, but setting up the SVM takes a really long time. And so there might be opportunities where what you really want to do is partition the computation and not the data. But for almost all the systems we're going to look at, the systems are going to slow down as a result of the increase in data size. So dividing the data is going to be sufficient to divide the underlying computation. Does that make sense?
Mm-hmm.
Okay, so how do we divide data? Anybody ever have to partition data across a bunch of machines or shard data across a bunch of machines? No, not so much. Let's imagine that we had a bunch of machines. Look, there are some now. And what we would like to do is maximize our speed up. So we have some job X, and we figured out a way to put it on all these machines. What are some important things that we can say about the way we put it on a bunch of different machines? What are the desired properties of a partitioning or sharding algorithm that will allow us to do work the fastest? Yeah.
Should be relatively even.
Yeah, so like uniformity is super important. Why do you say that?
Well, because then if it's not even one machine, it's our fault.
Exactly. So the machine that has a little bit more data than everybody else will surely be what's called the straggler, right? They'll complete a little bit after everybody else, and the runtime of the entire computation will be bounded by the performance of the straggler. Yeah?
Maybe a bit of a stupid question, but does X represent all the data?
X just represents the job. So the job, so the data and the program to run the data or something. You know? Just some, but the idea is that X is fixed. You know, we're thinking about maybe scaling up computers and we're not changing X. X is just a bit of work to do. Right? So D could be a list of numbers and P could tell you which ones were prime or something like that. I don't know. Right? Yeah.
What about some sort of metadata so you know how to put it together again?
Well, I think, yeah, like, let's dig up. So why are you concerned about being able to put it together again?
As far as like ease of use and like how fast you can kind of.
Yeah, I mean, I think at least in the simplest sense, once I have spread the data around, it would also be really desirable to know cheaply where a particular data item is.
Right.
So let's say that there was a variable Q that matched to exactly one of these servers. Let's say it was this one. It would be cool if whatever partitioning or sharding scheme I chose also made it easy for me to determine 1, 2, 3, that Q was on server 4. Because otherwise I'd have to like look at all of them. Right, so sometimes another thing that I would want, I would just say colloquially, I would like reads to be cheap. I don't want to have to linearly scan all the servers to figure out where the hell I put something. Right, and by a similar token, I would like my writes to be cheap. I would like to very quickly, somebody comes in and they say, I have this data item, L. And you want to just be able to be like, in order 1, you want to be like, L belongs on server 5.
Mm-hmm.
Right? So, what other properties might we want? Yeah.
I guess this one's kind of related to cheap reads, but you'd probably want data item on multiple different instances.
Well, no, I strongly disagree. I mean, I think we probably want, and maybe I didn't write this on here, but I'll write it on here anyway. We actually want a one-to-one mapping between data items and servers. If we didn't, first of all, reads and writes might not be cheap. Now, obviously we want our system to be fault tolerant, but replication would really be a separate concern. We can imagine each of these shards having multiple replicas, but we wouldn't want our partitioning algorithm to reason about those replicas, right? The partitioning algorithm would just say, Q belongs on shard 4. And if shard 4 is replicated 3 ways, that's great. So now Q's in 3 places, right? But the partitioning just says it belongs in logical shard 4. Thinking about replication and placement will probably be too complex for a sharding program. So we want a one-to-one map. Right? That is to say, every data item belongs in exactly one logical place, even if it might appear in multiple physical places for fault tolerance reasons. Yeah.
Is it desirable to make it cheap to rebalance the partitions?
Yeah. Well, yeah. So like, that's great. So I was going to get there last, but I'm glad you said it. So this is what you might call stability, right? So let's imagine that I lose a machine, or I add a machine. We would like it, if possible, for it not to be the case that literally every data item needs to be shuffled around the whole network. Right? We don't want it to be the case that, you know, I have A, B, C, D, and E, and then I have F, and we're still a little, we got a little skew here. So, oh crap, we better add a new server. We would like it to be the case that if you add a new server, this happens, as opposed to,
I see.
which sucks my ass, right? Because we just did all of the work every time we add a new server, there's more all of the work to do, right? And this matters a lot in like the distributed systems cloud, IoT world, where the expectation is that servers are going to be coming and going. There's going to be a lot of what's called churn, right? And so you want a system that's resistant to churn, that the cost of losing or adding a machine is not like tripling your work all the time, right? So that's great. So these are all things we want. So now it's going to be like, okay, well, let's go in search of an algorithm or a set of algorithms that satisfies as many of these desired properties as possible. It can be hard to find one that satisfies all of them. There's one other thing that I would point out. What else? It's related to cheapness, but and what else would you want?
You'd want it to be deterministic in how it allocates items, right?
Well, I would argue, this is what I would argue. If it was deterministic, we're probably going to get these for free. But there might be benefits to having less determinant. So for example, I haven't gotten into the mechanisms, but one mechanism might be, there's a directory service called D. And D knows how many machines are in it. And you ask D, what's the best place to do? Which might mean that in a different execution, D might give you different answers. Maybe that's okay. But maybe this has other disadvantages. But D would get us very uniform allocation, because it would know like the right place to put everything, right? So I would say that like determinism, it's always the case. Determinism is nice because it means it's easier to think about what the hell is going on. But it's not a necessary thing. Yeah.
Wouldn't we want fault tolerance as our last property?
Well, no, because as I argued before, like we already know how to do fault tolerance. All we've studied in this class is fault tolerance. So if you treat each of these shards as your whole system, we know how to replicate that system with primary backup. We know how to do paxos between these things. Like, in some sense, that's orthogonalized from the problem of data placement. Or I would like to argue that, but obviously the devil's in the details. But I want to keep our partitioning algorithm fault oblivious because we know how to take something that fails and turn it into something that's less likely to fail. Yeah.
Failure.
Huh?
Cheap failure gave you one back from something that doesn't work.
Well, I think that stability gives us that, right? That if we know the cost of the membership changing is relatively low, then we're a pretty recoverable system. So one other thing I would add
Like cheap
is, sorry?
Oh, sorry. Like cheap validation, maybe?
Validation of what?
Well, if you are computing something that it's correct, or I don't know. I'm just.
I would like to say that that's sort of orthogonal to the placement problem too.
Oh,
like
placement.
without saying anything about P, just
Wow.
assuming P is programmed P. We didn't say anything about it. All these problems are there.
Okay.
Now we would also like P to like be able to check its work efficiently. Yeah.
Stability includes adding new.
Yeah, adding and removing. Yeah. And obviously removing only works if we have replication, because otherwise we lose the data, right? So the other thing I was looking for was scalability, which I know this is a word that's super overloaded. what I mean by scalability is, my expectation would be that in a system like this, over time, the data size might keep increasing. And the number of servers might keep increasing.
Okay.
And I would like it to be the case that all these other things, like the cheapness of my reads, the cheapness of my writes, blah, 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 don't get slower as the metadata for the system gets slow. So for example, my directory thing seemed pretty cool. But the problem is that my expectation would be that at best, I would have like a log n situation. I wouldn't have like constant time operations, right? But it's going to turn out that there are ways to get constant time operations that are independent of the amount of data that we put in our system and the amount of computers that are in our system, which is good. Does that make sense? Yeah.
Question, why don't we get scalability for free when we get stability? It's like, why isn't that?
Because there's a difference between the amount of work that needs to get done in terms of data movement to react to a change in the membership
Okay,
versus the amount of work that needs to get done to look things up and place things
I see.
as a result of the size of the metadata.
Oh, okay, I see.
Right? So they're both concerns about, as the system is more dynamical, is it okay? But this one is like, if nodes go up and down, do you keep thrashing? And this is, as your data sizes increase, do your basic operations just go slow? And you would like it to not be the case. You might be willing to pay a log n cost. So, those are the properties that we might like. And that you might like in homework 4. What are some of the mechanisms that we might use to enforce these properties?
Question, actually? I wanted to clarify scalability. So if we did employ your directory like service, you know, so that it knows where to put what, as we scale up, it would be bottlenecked by D? Is that what
Yeah, well,
you're
like D, and D could be a distributed system too, right? So what does D need to manage? It needs to manage M, the number of data items, times, potentially in the limit, N, the number of servers. That's its like memory footprint, right? Because it knows where every item was placed on every server, and it knows about every other possible placement choice. So this is obviously increasing fast as M and N increase.
Okay, yeah.
But what we would like is that the lookup time to decide where to put something, for example, or where to find something, doesn't increase as that number increases, which would suggest that a directory-based approach is never going to work. Because best case, we're going to have like a B tree or something like that. So we're going to have like log
So
n.
it's possible.
We would really like order of 1 for these two things, right? Amortize. Yeah.
So that makes me think we want some sort of hash table to know where.
So that's great. So I think like that's the workhorse of partitioning is hashing, right? So I'm actually going to try to write a little matrix here and say, okay, uniformity, cheap reads, cheap writes, stability, and scalability. Mechanism. So let's talk about that first, because really, you're kind of jumping to one of the best answers, but who is familiar with modulo-based hashing? Who is not familiar with hashing? Okay, some people are. Okay, so let's imagine that I have this set of servers, and they're numbered. So I got 1, 2, 3, 4, 5, 6, 7. And I have some data item that comes into the system, and I want to know where to put it, or equivalently where to find it, right? So I'd say I have some access to some hash function, h, which takes a value of arbitrary type, let's just say it's a string, and returns a number. Right, so we have this function h. So we have this value, let's say the data is the string Peter. And I want to just place this on one of the replicas. And I want to have the property that as I keep placing different people's names on the replicas, they more or less get spread out uniformly and all these other nice properties. So say, okay, well, the hash of Peter is some number. I don't know, 15. Hash function just is a function that takes inputs and produces integers with the property that those integers are roughly uniformly distributed. And it's pretty hard to predict what integer you're going to get for a particular string. And in the fullness of time, if we hashed all the names, it would roughly uniformly cover the integers. That's, hash functions are really hard to understand how they work. So I'm not going to try to talk about that here. I don't understand how hash functions work. Does anybody understand how hash functions work?
It's all.
Like, how do you look at two hash functions and be like, this one has better mathematical properties than this one?
No.
Nobody knows. Well, some people. Sesh might. I don't know.
Sesh might know.
Sesh probably knows. I mean, or he knows somebody who knows.
Yeah. You say it for Sedgwick.
But 15 doesn't help us very much, right? Because 15 isn't one of our numbers, but the obvious thing to do is we hash it to some number to be an astronomically high number, and then we take the modulo of that and the number of buckets in our system. 15 mod 7, which is what? Because I suck at this. It's 1?
No.
Or is it 8?
Oh, yeah, crazy. 7 times 2 is 14. Oh, sorry.
It's 1, right? It's 1.
Okay.
How many times does 7 go into 14? It goes in 2 times, and then there's 1 left over, right?
Okay, I can do math.
Okay, so, no worries. I mean, I'm terrible at this.
Turns out none of
That's
us
why I had to talk it through. What?
Turns out none of us understand.
But we understand the idea of doing modular arithmetic, right?
Yes.
If we keep doing this, we're gonna more or less uniformly start hitting the numbers between 1 and 7, even though these are hitting all kinds of crazy numbers, right? So what do we get there? Well, the coolest thing that we get is we totally get order of 1 reads and writes. Because you just call the hash function on your input. It does not matter, and we totally get scalability. Because it does not matter how many inputs there are. This takes as much time as it takes to do the bitwise math to get this number, and then the math to get this number. It's a constant time operation, irrespective. Now, as the size of the string increases, pay a little penalty. That's not right? Good. So let's see. Hashing is it uniform? Big time.
Basically.
Is it cheap reads?
Yeah.
Is it cheap writes? We already said it was scalable. What about stability? Ruh-roh. Yeah, so it's not very stable at all, right? Because in fact, we would see the exact same thing. By expectation, if we change, so what happens if we add a new server? We add a new server, guess what? We're changing the number that we're doing our modular arithmetic on. So you imagine if I've written down a bunch of these things, Peter hashed to 1, you hashed to this other thing. By expectation, if I change this figure, all the buckets change. So by expectation, almost every data item has to go to another server in the event of a rehashing. So it sucks with respect to stability. Now you might not care. You might be like, dude, n is 3.
It'll always be
I
three.
take really good, I love these things.
Yeah.
I pamper them, I take really good care of them, I read them poetry. None of them are going or coming. So I don't care. Because I'm almost never going to do a rebalancing. In fact, in the world of databases, this is always what you do. You do hash partitioning, you buy enterprise class machines, you got 6 of them. If they go down, you try. Somebody gets fired. And so, what are some of the other things we could do to try to, for example, do better around stability at the cost of other things? Let me just throw one out there. I could just, I could do that. I could I could flip a coin, or roll a die between 1 and 7. So let's analyze that. Would that give me uniformity?
Yeah.
Probably better than hashing, actually. Or at least as good as hashing, right? What about cheap reads? Why?
Because it's in a range.
It's where the hell is it? It could be anywhere.
You have to check everything.
Yeah, you kind of have to check everything. You build an index over it, and then you run afoul of scalability stuff, right? So that's not great. But what about writes? Yeah, super cheap, maybe even cheaper than hashing. Stability, I think we're good, right? Because everything's randomly placed. And so if you add some new things, you could randomly pick things to get moved to the new server, for example.
Could you re-explain why reads are bad and writes are cheap?
Well, because if what I do is I get Peter, and I'm like, where does Peter go? Fucking, I don't know, 5. So Peter's on 5.
Okay.
Now somebody wants to go read Peter.
That was random.
Where's Peter? I don't
have to check all
know,
of
like,
them. Okay.
do you have Peter? Do you have Peter? Do you have Peter? It could be like a linear
Okay,
search.
okay, got it. And then writes.
But writes are super fast because, like you just saw.
Oh, you just
Like I was just like,
compute
I
the
don't
random
know, by
place.
fiat, I don't know, it's 5. I don't know.
Got
So
it,
we're,
got it,
we're
got it.
supposing we're just writing a new element. We're not worrying about overwriting a specific element that already exists.
Oh, so that's a good one. Yeah, so in that case, but that's fine though, because then Peter might end up in multiple places, which is fine, until I go try to read it, in which case I gotta go read everybody, but we already had to read everybody, right? So that's fine. Yeah, so you can place it on the same item. And then what about scalability? Yeah, it's
It's
fine.
actually fine.
I mean, it's fine subject to this sucks, right? And it gets worse. But it's not going to depend on the size of the input domain. Right? Okay, what else? Well, we could do, what else could we do?
Guess you could do an order, maybe.
Yeah, you could do round robin, right? So, similar to everything else we've already looked at, the expectation was that this would be perfectly goddamn uniform, assuming you didn't remove it or anything, right? Everybody has exactly the same amount of stuff if you've gone around all the way. And that's not looking that great. You could imagine trying to remember where something was, but it would be hard, right? Because the state you need to do to make writes fast is super easy, right? You just remember one bit of state, right? Or whatever, the last guy you did the write to. But in order to go back and make the reads fast, you need to do some kind of cunning data structure over that. So that seems like super hard. So I probably wouldn't want to do reads in a round robin issue. But what about stability? I could make a similar argument that I made about random, that there's patching up stuff you can do. Or I'm going to do a half cross for these, actually. It's not great, but it's not so bad. And scalability is fine, subject to the concerns around. So, am I forgetting anything? Oh yeah, well let's not forget, what if we have a directory? Well, we could do killer uniformity in that case. We could do killer stability in that case, right? Because we could look at the directory after it changed to the network and be like, oh, I know exactly what data item, I can move exactly the minimum number of data items to rebalance the cluster, and not one more. Right? So that's killer. Yes, reads could be fast, but we're not looking at order of 1 anymore. And yes, you can make writes fast. We're not looking at order of 1 anymore. And then, this is where you're really going to get a hurting.
Mm-hmm.
Yeah.
Could you clear up stability and scalability?
Yeah, sure. So stability is, as nodes come and go, how much data needs to get shuffled. If I add a node, let's say I add a new node. Well, guess what? I'm not satisfying number 1 anymore. Because there's this one node that has no work, and there's the other nodes that have all this extra work. I'm not getting any benefit from the extra node. So what do I want to do? I want to move some of the data over here. Stability is, I would like to move the minimum amount of data around the network to get uniformity back after a change like this. An approach like hashing will move all of the data around and not be stable. Okay? And scalability is, as my data set and my set of nodes increase, does the performance of all these operations go down? So as I just said, if I have a directory, it tells me exactly where everything is. When I want to write a new thing, the directory can tell me exactly the best place to put it. But that directory needs to know all of the players and all of the data. And as those two things increase and are multiplied by each other, the performance of doing reads and writes in the directory is going to go down. Even if we have perfect indexing, we're still looking at log n rather than order 1. Does that make sense?
Yeah.
Thank you.
Can you explain
Well, yeah, that's what I just said. So I have this new data item, Peter. So we looked at, I could hash Peter and get a number. I could pick a random number. I could just keep sending it to the next guy. Or I could instead of doing H of Peter, I do lookup of Peter. Where I actually literally go out to the directory and I'm like, what partition should Peter be on? And it's 5. Why did it say 5? Well, it might say 5 because it had already put the Peters on 5. Or it might say 5 because 5 is the partition that is the least loaded. But in any case, it can make the best possible decision about how to keep things uniform. Right? It just isn't going to be scalable as those pieces of input increase. Is everybody on the same page?
Mhm.
Good. Wouldn't it be cool if there were a line here that got X's all the way across?
Yeah.
Anybody have a guess about what it might be?
What if you mix them all up?
What'd you say?
What if you mix them all up?
Like,
What if you
use
use,
some of each.
yeah.
That's some good systems thinking there. In favor of that. Yeah.
Is it a variant of hashing where you'd also have a directory of some sort?
That's an interesting idea. So that would be a hybrid approach. I'm not familiar with any such solution, and off the top of my head, it's not clear how. It could maybe because I'm not being creative, but it's not clear how they would ameliorate each other's weaknesses. Like in some sense, you feel like I don't know. Yeah, no, I've never thought of it. I'll give you a hint. You've read about it. Yeah,
Oh, is it the one from the diagonal thing?
that's correct.
Or the consistent hash?
Yeah, so consistent hashing, which I think I'm not going to have time to go over today, but that's okay, because it's kind of a long discussion. We're going to go over in the abstract, I guess, on Monday, and then we're going to go over more concretely when we read the Cord paper, which is a distributed hash table that uses consistent hashing. It's like one of the first academic pieces of work that demonstrated the benefit of consistent hashing. But you're right, Dynamo uses consistent hashing. So the idea of consistent hashing is to get something that looks like hashing, but which moves the theoretical minimum number of data items in the event of a rebalancing.
Wow.
At a really high level, because I think I have a moment to be really high level, the way that it's going to work is we're going to use a hash function, just like we did in regular hashing. But instead of just hashing the data items and placing them on servers using a modulus operation, we're going to imagine the data and nodes being hashed into a space, places on the unit circle. And so we're going to say this is like the unit circle mod some large, 2 to the, I don't know, 2 to the some big cat. Right? And so we're going to have a hash function just like we did before, but instead of using the hash function just to decide what numbered server a piece of data goes on, we're going to hash the data and the servers. So for example, we're going to say hash of Peter is, I don't know, 16. So here's 16, and here's where Peter should go. It's a data item. Hash of Emily should go to 187, which is like, I don't know, 187 Emily. And hash of Brian should go to 241. Okay, so there are our data items on the unit circle. And then we say, okay, well, here comes some nodes. So this is node A, and the hash of A is 28. And here's another server, the hash of B is 160. The hash of C is, I don't know, 200. And what can we do with this? Well, now we could say that a data item belongs on the server that is its successor on the ring. So Peter belongs on A. Nothing belongs on B, because there's nothing in this interval. Emily belongs on C. And Brian belongs on A.
Yeah.
See, so we've hashed the things, and we've hashed the places. And we've come up with a visual sort of analogy for where something belongs. It belongs at the next thing after it on the unit circle. And we know there's always something after it because it's a friggin' circle. Right? So you go around and you go pass home, and you'll find somebody. What this means is that if I add a new node, for example, I say there's a new node, let's say hash of D is, I don't know, 250. 250 D. The logic is that the keys that need to be remapped is not all of the keys in the system. It is the keys that would have been assigned to D, right? So the only thing that needs to happen when we add D is we say, well, shoot, D and not A is the successor of Brian. So A needs to give Brian to D. Right? So we added a server, and instead of having to rehash 3 things, we had to rehash 1 thing. Does that make sense?
Yeah.
Consistent hashing, by hashing the things and the places where things go, gives us a way to minimize. There's always going to be, or somebody goes away, right? Somebody goes away. A goes away. He's crashed. What happens? Well, shoot. Everything that A was responsible for, B is now responsible for. Peter had to get moved. Now, obviously, A had better have had a backup, or Peter was gone. That's orthogonal to this data placement thing. Make sense? So we'll go into this in much more detail. But that's kind of like the high-level idea. Is hashing is great because it's uniform and it's order of one, and it has all these great properties, but it sucks at stability. But this ingenious device of putting them into the same sort of metric space solves the stability problem. Yeah.
So you pick some K when you design your system and you read this that?
Absolutely. But so you pick some really fucking big K.
Yeah.
Yeah.
This is just like anything like this. How big is your word? Right? And you might have to revisit that at some point, but it's going to be like really far in the future.
So something big.
You're absolutely right. The expectation is you do not change this. And I will point out one more thing is that in practice, you probably don't want to do this for the assignment. Because the number of keys that we're going to put in your thing is not going to be so big that stability is going to be a big thing. And this is much more complicated than hashing. And if the number of keys and buckets is small, this doesn't do that uniformly. So the trick that you saw in Dynamo was, instead of having hosts, we're going to create these things called virtual nodes, where there's like hundreds of virtual nodes for every host, and map the virtual nodes into the unit space, so that you have some kind of opportunity to get a better distribution. So if any of you are ambitious, a great many students in past offerings in this class have done consistent hashing. Many of them have had a bad time. If you do decide to be ambitious and go this route, look into virtual nodes, because otherwise, for small k, or for small m, this isn't the most uniform thing. Regular hashing will do better. Yeah.
So by that you mean like you're going to run nodes A, B, C, and D.
Yeah.
And virtual nodes meaning
Just
like,
logical buckets,
logical
where there's
buckets.
many
And
buckets
50
per,
buckets.
yeah, and the same number of buckets per node.
Right. Okay.
And then you're thinking about shuffling buckets among the nodes. Because otherwise, like, if there's only 3 things, the likelihood that they're placed at these intervals on the unit circle as a function of your hash function is like really low. And if they're not, and then, you know, like, you're not gonna have good placement, right? If like, imagine they're like here. Well, you're in a world of pain, because this guy's gonna get all the data.
Yeah, that's why I asked, because K obviously has to be matched up to the number of nodes you pick.
Exactly. Okay, so I think that's it. Happy, yeah, one.
So for that table, the one for consistent hashing, is there anything that consistent hashing does worse than?
Oh, thanks for letting me, no, so consistent hashing kicks butt. With, you know what? With the caveat I just said, you may need to play a couple tricks to make sure that it's uniform for small m.
But for big M, it's great.
For big M, it's great. So the trick is make m big, which is what virtual nodes do.
Okay.
Cool.
We have a few minutes left, but any last questions or questions about the homework?
I thought you said any last words.
How likely are we going to get any sort of feedback on previous assignments?
Oh, well, so, you know, so for homework 1 and 2, both of which the grades are back, you can go ahead and ask the TAs for detailed feedback on how they were graded. Sure.
Okay.
My expectation is that the answers to those questions for homework 1 and 2 are not going to be particularly interesting, but for homework 3, it's going to be extremely interesting. So I encourage you to take advantage of that section time to talk through the TAs about exactly what went right and wrong in your assignments. I think that, like, in some sense, homeworks 1 and 2, we're just getting you up to speed to build homeworks 3 and 4, and homeworks 3 and 4, where you get the opportunity to apply what you've learned in this class to something that is, in my opinion, really hard, right? So I think you should leverage the expertise of the TAs. And certainly feel free to ask me too, although I might not be able to have really detailed answers about why the TA wrote X or Y, because I didn't actually perform the grading, but I know what I expected, yeah.
Could we get the test scripts for homework 3 that weren't released?
Say again?
Could we see the test scripts that weren't released for homework 3?
That's a question for the TAs. I mean, I think, like, in general, it should be okay, because we expect the assignments to be different enough every year that there won't be any incentive to cheat. But I would leave that up to the discretion of the TAs, so I would ask them. Yeah.
So I think the Dynamo paper also mentioned another hashing algorithm, pastry.
Well, pastry is a DHT that is sort of an inheritor of Core, and pastry also used consistent hashing. But pastry is a whole application. So pastry also uses consistent hashing. It's not like an alternative to consistent hashing.
DHT?
Distributed hash table.
Oh, okay.
It's like these really important data structures from the early days of peer-to-peer computing.
Sure.
Hey, wouldn't it be cool if you like had a hash table only running on thousands of computers all over the internet. Turned out it wasn't that, but it was a cool thing to study. Also, I just got this quote. So this guy, Gertrude Scholem, who studied Jewish mysticism, was introduced to the New York Jewish Scholars Society. That's really famous. I forget what this guy's name is. And of course, Kabbalah and mysticism was like frowned upon. The guy introduced me and says, ladies and gentlemen, garbage is garbage. The study of garbage. Scholars. Introduces the guy.